Good morning, one and all. This is Pujita Anansoy from CSSC holding a roll number 19951A05C9. Today, my presentation is about reducing leakage energy via exploitation of cage generational behavior. Introduction. Power dissipation is an increasingly pressing problem in high performance CPUs, although power used to mainly be a concern in battery operated devices. Thermally, reliability and environment concerns are all driving an increased awareness of power issues in desktops and servers. Most power dissipation in CMOS CPUs is dynamic power dissipation, which arises due to signal transitions. In upcoming chip generations, however, leakage power, also known as static power, will become increasingly significant because leakage current flows from every transistor that is powered on. Leakage power characteristics are different from dynamic power, which only arises when signals transition. As such, leakage power warrants new approaches for managing it. Power background. As CPU chips are more densely packed with transistors and as clock frequencies increase, power density on modern CPUs has increased exponential in recent years. Although power has traditionally mainly been a worry for mobile and portable devices, it is now becoming a concern in even the desktop and server domains. In CMOS circuits, the dominant form of the power dissipation is dynamic or switching power. Dynamic power is proportional to the square of the supply voltage. For that reason, it has been common to reduce supply voltage to improve both performance and power. While effective, this optimization often has the side effect of increasingly the amount of static or leakage power that a CMOS circuit dissipates. Leakage power and cage generations. Because cage compromise much of the area in current and future microprocessors, it makes sense to target them when developing leakage reducing strategies. Has shown that transistor structures can be devised with which limit static leakage power by banking the cage and providing sleep transistors which dramatically reduce leakage current by gating of the VDD current. Potential benefits. To motivate the potential of our approach, we start by presenting an idealized study of its advantages. Here we have run simultaneous simulations using an oracle predictor of when dead time starts in each cage line. That is, we note when a cage item has had its last successful hit before the cage miss that begins the next generation. We imagine in the section only that we can identify these dead periods with 100% accuracy and eliminate cage leakage during the dead periods. The above table is the processor core and memory hierarchy configuration of simulated processor. Methodology and modeling. Simulator. Simulations in this paper are based on the simple scalar framework. Our model processor has sizing parameters that closely resemble alpha 21264 but without a clustered organization. Benchmarks. We evaluate our results using benchmarks from the specific CPU 2000, the Standard Performance Evaluation Corporation 2000, and media bench suits. The media bench applications help us demonstrate the utility of cage decay for applications with significant streaming data. The benchmarks are compiled for the alpha instruction set using the compact alpha compiler with specific peak settings. Evaluating power trade-offs. A basic premise of our evaluations is to measure the static power saved by turning off portions of the cage and then compare it to the extra dynamic power dissipated in our method. Our method dissipates extra dynamic power in two main ways. First, we introduce counter hardware to support our decay policy decisions, so we need to account for the dynamic power of these counters in our evaluations. Second, our method can dissipate extra dynamic power in case where our decay policy introduces additional L1 cage misses not present in the original reference stream. These L1 misses translate to extra L2 reads and sometimes also extra writebacks. Turning off a dirty line result in an early writeback which is extraneous only if paired with an extra miss. For the rest of this paper, when we discuss extra misses, we implicitly include associated extra writebacks. Thank you.